Thank you. Thanks very much for the invitation. It's great to be here. Okay, so indeed, we're going to try and count rational curves on Calabi-Yau manifolds, and we're going to do it via categorical information, homological mirror symmetry. So this is joint work with Sheridan and Ganatra and Nick Sheridan. Nick is going to talk about the same subject on Thursday. He will pick up from where I leave off, so I will be able to say almost nothing about proofs, and he will actually tell you the idea about how you prove things. But the aim is to work towards a new proof of the mirror theorem of Giventhal and Lian Liu Yao for the case of Calabi-Yau hypersurfaces in projective space. So this is a result about counting rational curves on such Calabi-Yau manifolds and interpreting those counts in terms of certain sort of integrals of holomorphic volume forms on a mirror. And so our proof is very different from the old ones. It goes via homological mirror symmetry. And without actually explicitly computing Gromov-Witten invariants or period integrals, but rather just saying that they're equal. So let's take a mirror pair of projective Calabi-Yau manifolds. Really, these will be families over punctured disks. Families of Calabi-Yau manifolds. And so this will be a pair as sort of certified by some authority. Maybe Batirev, Borisov, or so there are numerous constructions in the literature of mirror pairs which typically come with dual pairs of Lagrangian torus vibrations, or at least they ought to. So in terms of the sort of data that you have, well, for my purposes, it will look something like this. So on the A side, the symplectic side, we'll have, well, actually, so the A and B sides will, for the moment, look indistinguishable. We'll have so delta star is the punctured disk, and we'll have two smooth, two proper holomorphic submersions. So families, smooth families of complex manifolds. and with fiber dimension n. And these fibers will be Calabi-Yau, so they'll come with Calabi-Yau data. That's to say, they'll come with volume forms. So omega on x and omega check on x check will be holomorphic n forms that are non-degenerate on the fibers, positive on the fibers. And for my purposes, I want to think of both of these as projective families. So I want to think of having very ample line bundles, L over X and L check over X check, so that one can think of these families as sitting in projective space. So more precisely, one has X sitting inside the disk across some big projective space relative to the punctured disk, and similarly for X check. Okay, so that's the sort of data that I have in mind. So this is symmetric, and I'm thinking of mirror symmetry as sort of acting in an involutory fashion on some class of data like this. So the data we'll actually need is, however, asymmetric. More or less it comes from, it's sort of subsets of the data that I have here, though that's not going to be precisely true. So on the A side, I'll take X, which is X sub B, a generic fiber. This will come with omega, a Kähler form that's inherited from the ambient projective space. So that will be my symplectic manifold. So this is an integral Kähler form. It represents the first Chern class of L, but I actually want a bit more data. I want to choose. I want a holomorphic section of L, giving me an actual divisor D, whose homology class is Poincare dual to omega. So that's a bit more information. It has something to do with putting a central fiber in on the B side. For reasons of technical convenience, rather than because it's sort of necessarily true, I want to assume that D is of a nice form. So I want to assume that D is a normal crossing divisor, so it has components dj which individually are smooth, and so it's they intersect transversely. So it's a normal crossing divisor, and moreover, beyond that, I even want to assume that each component individually represents some positive multiple of the symplectic class. Okay. So it will naturally be the case that on the complement of the divisor, the Kähler form is exact. It's d theta. So that one form is going to be important, and theta should link each dj positively. So its integral around a little loop, positive loop encircling dj, which should be positive. The last thing on this side is to say that this is a Calabi-Yau manifold. All that will be important there is that C1 of the tangent bundle will be 0. In fact, omega will determine a homotopy class of trivializations of the first Chern class. Okay. So that's the data that I extract on the A side. I forget about the rest of the family I had. On the B side, I do something different. There are a couple of things to say here. One is this. So I have monodromy of my family, so T, which acts as an automorphism of the cohomology of a generic fiber. And there's a remarkable theorem in complex algebraic geometry that says for projective families of fiber dimension n like this monodromy satisfies the following. There's some k with the property that t to the k minus the identity is nilpotent of order n plus 1. For mirror symmetry to stand a chance of being relevant here, you must have what's called maximal unipotency of your monodromy, which means that k is 1, so t minus I is nilpotent of this order, but it's nilpotent of exactly that order, so t minus I to the n is non-zero. So somehow that's expressing the idea that your fibers are really degenerating very much in the limit as you go to 0 in the disk. Okay, so this is, for us, this is an assumption. Okay, that's an input for us. So the other thing that I want to say about the B side is this. So you can take a kind of Laurent expansion of X check, by which I mean you can think of this as being defined by equations in projective space, which so that for any fixed parameter q in the base, they're algebraic equations, and they vary holomorphically in q in delta star. And so you can sort of take a Laurent series expansion, and what you get is equations, projective equations with coefficients in a field of Laurent series. So what you get is a projective, smooth, algebraic variety, X check alg, over the sort of formal version of the punctured disk, which is the field C double brackets Q of finite tail Laurent series. Okay. Yeah, for me this is actually a scheme. Well, so there's not much difference between a scheme and a formal scheme here, because I'm working with things that are projective, and there's this theorem of Grothendieck that actually tells you that projective formal schemes are schemes. On the other hand, one might. Oops. What's going on? One might decide that it was a good idea to do things with some sort of rigid analytic spaces, and we're not addressing that idea. So there's this famous conjecture of Kontsevich from '94, which is that mirror pairs, understood in some geometrical sense of T-duality, should satisfy homological mirror symmetry. And furthermore, that this should be a kind of organizing principle for mirror symmetry statements. This should be a sort of a root of other statements having to do with holomorphic curves. So let me give you a brief statement of homological mirror symmetry in a version tailored to the present context, not entirely standard, though close to it. And it's the following. So I'm going to take the relative Fukaya category, so I'll say a little bit about it in a moment, of x relative to d, so some sort of Lagrangians, and I'll take the derived category of coherent sheaves on x check algebraic, and, well, roughly speaking, I want to say that these are equivalent. I'll have to decorate this side a bit for that to be even remotely reasonable. Okay, my first decoration is an MC. That stands for Mara-Cartan elements, also known as bounding cochains. And if you haven't encountered this notion, I'd recommend you ignore it. And then I'm going to do some sort of a formal algebraic process. This is going to be the split closed twisted complexes, something that has no geometry, a process that has no geometry in it. And so this thing is going to be, this is an A infinity category. This thing here, I write, so this is the usual notation for the derived category. I really mean a a differential graded model for it. So it's a differential graded category, which is an example of an A-infinity category. And so one thing about this equivalence is that it should be an equivalence of, a quasi-equivalence of A-infinity categories over the field of Laurent series, finite tail Laurent series. This, after all, is a variety over that field. So its derived category lives over that field. It's a particular feature of the relative rather than absolute Fukaya category that it can be defined over this one. Before I sort of get into anything about what these are, so this is an equivalence that respects weak Calabi-Yau structures. What does that mean? So weak Calabi-Yau structure on an A-infinity category C means that if you take C and think of it as a bimodule over itself, and you compare it to the dual bimodule with a degree shift, there's an equivalence of an isomorphism of bimodules. Okay, so let me unpick this a little bit. So first of all, the objects of this one are exact, so theta exact, compact, spin graded Lagrangians in the complement of your divisor, and the Homs from one to another is the Floer complex, which in this context means that I take this base field and I take that, so I take a vector space whose basis is the intersection points of my two Lagrangians, supposing they're transverse at least, and then the A-infinity structure involves holomorphic disks bounding various Lagrangians, and those are counted with powers of Q that record how many times they hit your divisor. One of the features of Lagrangian Floer cohomology is that you have a duality like so. So intersections of L0 and L1 are the same, of course, as intersections of L1 and L0, and that idea gets elaborated into a pairing like so. So that's the weak Calabi-Yau structure. There's a pairing involving holomorphic curves that sort of look like, with boundary conditions L0 and L1 like this, which pairs this thing with this thing. So the weak Calabi-Yau structure is just intrinsic to this category. The objects of the derived category of the mirror I can take to be finite complexes of finite rank algebraic vector bundles, E on X check, and the Homs from one to another I can take to be, the check complex that computes, the check complex with coefficients in the sheaf of Homs from one to the other. So the cohomology that's a complex, and its cohomology is x's from E to F. And the volume form trivializes the canonical bundle, the canonical line bundle, and whereupon Serre duality says that x's from E to F are dual to x's with a degree change from F to E. And that's the weak Calabi-Yau structure. So the weak Calabi-Yau structure well, put it this way: the idea that homological mirror symmetry respects weak Calabi-Yau structure normalizes your volume form. So two basic problems are, first, how to prove homological mirror symmetry, and second, how to deduce other sort of closed string aspects of mirror symmetry from it. Well, our work sort of gives some progress on the first question. We have a reduction that says that it's enough to prove something simpler. But it does give us a solution to this one. And that's really the focus of this lecture and Nick's. So the whole story is based on a notion that we call core homological mirror symmetry. Okay. So let's take X and X check with all their attendant data as before. So, for example, X check has this maximally unipotent monodromy assumption. And so our standing assumption which is what I call core homological mirror symmetry, is the following statement. You're given some subcategory A of the relative Fukaya category, and you're given some subcategory B of the derived category of the mirror. They're both full subcategories, so you're given some, basically you're given some objects and the morphisms between them, and you're given a quasi-equivalence respecting weak Calabi-Yau structures of A and B. Okay? Furthermore, you're told that B is reasonably large, namely it split generates the derived category. So that's to say, every object in the derived category here is a summand in an iterated cone of morphisms from B. Okay? So that's core homological mirror symmetry. Okay. So everything I say will take the form, if core homological mirror symmetry holds, then something. Yeah? Well, I mean, so, the right mirror has the mirror map built in. Okay, that's what I mean. We'll get to mirror maps. So, okay, I guess I can erase this one. first of all, the generation theorem, which is theorem of Nick and myself, is that core homological mirror symmetry implies that not only does B split generate this one as assumed, but also A split generates this one. And so, consequently, full HMS holds. So, I guess I've given several talks about this, and several of you have heard such talks, and it's not going to be what we'll talk about this time, though it's certainly a key input to what comes next. What I do want to talk about, so this is Shiel, me and Nick, and this is, so this is in preparation, we're writing it up. It's that core homological mirror symmetry implies a Hodge theoretic version of mirror symmetry. So, namely, there is an isomorphism of modules over this field, vector spaces over this field. Lambda, I'll write it this way around, though maybe the other way would be more natural. So this is going to go from the even part of the small quantum cohomology of X. Okay, so this is just the cohomology of X with coefficients in this field, but it has more structure sort of lurking, ready to be used. So the even part of that. To the de Rham cohomology in degrees that are even modulo the middle dimension of the mirror family. So I'll write this as the algebraic de Rham cohomology. So this is like the de Rham cohomology of the local system of de Rham cohomologies of the fibers over the punctured disk. Such that the following holds. So first, lambda maps the unit of quantum cohomology to the volume form on the mirror side. So remember, the role of the mirror of the volume form here was that it was normalized so that the equivalence of these parts of my categories respected these weak Calabi-Yau structures. In other words, Fleur-Poincaré duality went over to Serre duality with respect to the trivialization of the canonical bundle that I get from my volume form. Okay, so that's a normalization of my volume form. And remember, you think volume forms that, they're defined up to scale. But here I have a lot of scalars because my scalars are Laurent series. Okay. So, what's the correct order? Yes. So second, if I look at, so second is the behavior of lambda with respect to natural filtrations. And you can say it like this. if I look at quantum cohomology in degree 2p, that's going to go to a certain part of de Rham cohomology, which is this one. So this is the monodromy, this is part of the monodromy weight filtration on de Rham cohomology, and I'll explain it in a little bit. And this is part of the Hodge filtration. A couple more properties. The third is that lambda respects wedge product pairing. So if I take if I take two elements of quantum cohomology and take their product and integrate, that looks like a quantum product, but it's the same as the classical version. That's the same as, up to some sign, as what I get on the mirror side under lambda. So, this is naturally an element of the Laurent series field. This one, well, you see, I'm integrating really over the fibers of this family. So it's a holomorphic function in Q, and I think of it as I take it to Laurent expansion. And the fourth, and really the crucial one, the most striking one, is this. So this one is about a comparison of connections, or differential operators. So D, capital D, is the operator Q d by dq minus quantum cut product with the symplectic class. That's an endomorphism, a C-linear endomorphism of quantum cohomology. Okay, so you see what I had was just a complex vector space tensored with C adjoin Q, so it makes sense to just differentiate things. This one is the Gauss-Manin connection in de Rham cohomology of the mirror. Remember, the Gauss-Manin connection is the thing that says that when you're looking at de Rham cohomology, it has a natural integer lattice sitting inside it that comes from thinking of it as just singular cohomology with z coefficients tensored by R. So it gives you a local system when you have a family of a local system in the de Rham cohomology of the families of the fibers of a family. This is the algebraic version of that, but it's the same deal. And it's in the direction of the vector field on the base, delta, which is always going to be Q d by dq. Let me make a note of that one. Okay. Notice that it's in stage 4 that holomorphic spheres make an explicit appearance. Okay, because I've got a quantum cut product here, so I have 3-point Gromov-Witten invariants. This is the middle one. Okay. So I'm going to unpick this statement a bit. To begin, I should make a couple of admissions or disclosures. We're writing this up. So one admission is that we've not yet done orientations and their attendant pesky signs. Though I think to a large extent we've done, what else we need to do. I'm just writing out the details. There's one other thing, which is that really, for 4, I should use not the Gauss-Manin connection itself, but rather something which is almost surely the same thing. So, but rather the image of Getzler's flat connection in periodic cyclic homology of the derived category under an HKR type, a Hochschild-Constant-Rosenberg type isomorphism with the Rahm cohomology. So there are these sort of 2 natural connections, and it's not yet in the literature that they're the same thing, though sooner or later I'm sure someone will sort that out. It's a purely algebraic geometry aspect of the problem. Okay. So the key example is the case of Calabi-Yau hypersurfaces in projective space. That's what X is. Where so for which Nick has already proved homological mirror symmetry. In fact, he didn't need core homological mirror symmetry. He used a slightly different argument and proved homological mirror symmetry. Except that I come to the point that Scheele raised, which is that Nick didn't quite pin down what's called the mirror map. So up to a change of coordinate, sort of sending the coordinate q on the base of the B side to some power series q primed, which is like q, so q plus a2 q squared plus a3 q cubed, and so forth. So he figured out that the change of coordinate has leading term, which is somehow the natural one that you sort of is sitting there on. So this is on the base of x check over delta star. Okay, so there's a completely explicit construction of your mirror family. It comes with a natural coordinate, which, however, is the wrong coordinate. You have to change it, and the coordinate changes some highly non-trivial power series, whose leading term is just q. Okay. And he didn't determine that. So this one goes up. Yes. Yes. Well, it would look like that, but it's not true. So one thing to say about it is that this is not just some abstract equivalence of this piece of the Fukaya category with some category. It's an equivalence with something that has strong geometric meaning, namely it's a chunk of a derived category of a nice algebraic variety, and it's a big chunk. And so, we leverage that information, and that's crucial, and that's somehow the thing that gets things going. This is very different to the story. No, it's just anything. You don't.
In the box, you're being told that the derived category of X check embeds in the Fukaya category of X. That's already. That's
correct.
A pretty strong relation.
That's correct.
Yeah.
Why not take X check to be a point always for every?
Well, that's one thing. Yeah. I guess it's maybe, it's it somehow has to be, maybe I should say it's a non-empty subcategory or something. But, yeah, it's surprising, but there's information there. So what I'll explain is that, where were we? Yeah, so we were talking about this example of mirror symmetry for Calabi-Yau hypersurfaces. And I'll explain that Hodge theoretic mirror symmetry implies that implies implies a normalization both for omega check and for this coordinate change. So Q has to be what's called a canonical coordinate. So essentially, so this statement implicitly pins down two sort of Laurent series parameters for you. They're somehow embedded in the Fukaya category. And so we therefore recover this mirror theorem, which, well, of Giventhal and Yan Yu Yao, which allows one to actually sort of get at curve counts in these Calabi-Yau hypersurfaces via mirror symmetry. So one corollary is as follows. So this concerns the Yukawa couplings. I'm going to phrase this slightly strangely. I wrote corollary, but I'm just going to write an argument for you. And it's this. So suppose I take what's called the Yukawa coupling of x, so which is the integral over x of the top quantum power of the symplectic class. Okay, so that's what the Yukawa coupling is. So this is something that has to do with counting holomorphic spheres. Well, let's see. So I can write it, of course I can write it as 1 times omega to the n. And that's the same thing as 1 times the operator d applied n times to 1. So remember that d was this one, so q d by dq kills 1, and so what I get is just, when I apply it to 1, is just omega stuff, is just omega. And I do that n times, there's a sign here. But now, that's the same thing as the integral on the other side of lambda of 1 wedge lambda of d to the n1 by property, I think that was 3. And now, that's the same thing as the Gauss-Manin connection applied n times to lambda of 1, and it fits in like that. Signs everywhere that I'm suppressing. So that was 4, and then by 2, lambda of 1 is my volume form. And that's what's called the B-side Yukawa coupling. Okay. And now at this point, there shouldn't really be a sign anymore. Okay, so you get that this count of curves is equal to this sort of period integral thing. And so this corollary is of most interest in the three-dimensional case. So for the case of the quintic threefold, X, the Yukawa coupling is, well, it's omega star omega star omega, but when you unpick that, you discover that it's just a generating function for Gromov-Witten invariants. So these are always genus-zero and degree d curves going through Poincare duals going through d at 3 mark points. And so this is really counting curves in a quintic threefold. So these are, this is some count of multiply covered holomorphic spheres. Okay. On the other hand, way back in, I think, 91, the paper that really introduced mathematicians to mirror symmetry, Candelas, de Ossa, Green, and Parks, were able to compute in full the B-side Yukawa coupling for this example. So, it starts with 5, and then you get 2,875 Q. That's the number of lines in a quintic threefold, and I can't remember how it goes on. So this number is something that we're getting at via mirror symmetry. So in higher dimensions, these Yukawa couplings are only a part of the story. The thing is, in higher dimensions, you don't just get generating functions for Gromov-Witten invariants like this, but rather certain products of Gromov-Witten invariants. So, and really you wanted to know the actual Gromov-Witten invariants. So in higher dimensions, there's more information about Gromov-Witten invariants in, well, the fundamental solution to the quantum differential equation. The quantum differential equation is the equation that says you're in the kernel of D, which is mirror to the Picard-Fuchs equation saying you're in the kernel of the Gauss-Manin connection. time. So I want to tell you something about normalizations. So you see, here I didn't use property 2. Property 2 had to do with filtrations. So I need to tell you a bit about that, because that's what's going to govern normalizations. So filtrations on de Rham cohomology. You know what? So time is short. I'm going to skip the Hodge filtration. You know, look it up if you don't know and care. I'm going to tell you about the weight filtration, the monodromy weight filtration. So I'm going to define n to be the log of the monodromy on acting in the cohomology of the generic fiber of X check. That makes sense because of this unipotency property. So it just means I take t minus the identity plus that squared over 2, and so on. And it stops at the nth stage because of maximal unipotency. So this is nilpotent of order n plus 1. And then linear algebra gives you the following. There's a unique filtration of de Rham cohomology called the monodromy weight filtration, which starts at a piece called W2n, and then I have W2n minus 1 inside that, and eventually W0, and then W minus 1 is 0, such that two things hold. The operator n takes you down 2 steps. Okay, and B, so as a consequence of A, I have the following. So if I look at the associated graded of this filtration, and I'm going to look at it in dimension in the middle degree plus some k, and now I can also look at it in the middle degree minus k, and then the kth power of n takes me from here to here by A, and I want that to be an isomorphism. Okay. So lemma, there's a unique filtration with that property. So e.g., so W0 is the same thing as the lowest graded piece. So it's then forced that has to be the image of n to the n, and W2n minus 1 is the kernel. Okay. And so then the first isomorphism theorem expresses B for this case. K equals n. So for the mirror quintic, one has that, well, so the middle de Rham cohomology is C4, so that's W6, and sitting inside it you have C3, C2, C, and this is W5 equals W4, this is W3 equals W2, this is W1 equals W0. Okay? So these are the monodromy invariant cocycles. So now I'm ready to tell you the key thing about normalization, and that'll wrap up. Okay, so first, normalization of the volume form. Remember, as things stand, this is just normalized so as to satisfy the requirements of homological mirror symmetry, which is highly impractical. But let's observe that if I take 1, which lives in QH0, and apply D to it, then I get the symplectic class, which is in QH2. And so lambda of D of 1, well, lambda of D of 1 is nabla delta of omega check, and that must now live in, by property 2 of the theorem, in W, not 2n, but W2n minus 2. Okay, so the property that this holds fixes omega check up to a C star scalar, it turns out. Okay, so this is the thing that allows you to actually get your hands on omega check in purely Hodge theoretic terms on X check. Okay. The C star scalar is a little annoying, but you can fix it by looking at the 0th order term in the Yukawa coupling, which is just the symplectic volume. So the C star scalar has to do with a normalization of the symplectic form on the A side. And you can also get at the canonical coordinate Q. So the mirror coordinate Q has this sort of remarkable property, which is the following. So let's observe that D squared of 1 is omega star omega, and that lives in QH4. And consequently, applying lambda, I get that, and applying property 2, I get that if I apply the Gauss-Menin connection in direction Q by dq twice to the volume form, I land in W2n minus 4. Okay, so that's the property that fixes Q, so you're not allowed to reparameterize Q anymore, up to a C star scalar. Okay, so, and now for the example of Calabi-Yau hypersurfaces, one can also fix that C star scalar because you see Nick, as I pointed out, determined the leading order term of the mirror map already. So those are the things that will allow one to actually count curves. Okay. If I may have 1 or 2 minutes, I will wrap up. So, So I've so far said just not a word about proofs of anything, and Nick is going to address it, but I feel I should just say a tiny, tiny bit. Where does this map lambda come from? So it comes as follows. So in algebraic geometry, you have this de Rham cohomology. And I'm going to adjoin a variable u of degree 2. And then it's known that that has an interpretation in terms of the derived category. So that's what's called the periodic cyclic homology. Of the derived category. There's a known isomorphism, which is some version of the Hochschild-Constant-Rosenberg map, composed with an automorphism of this that involves taking the wedge product with a square root of the Todd class of your manifold. So that's an isomorphism. And so really the thing is to understand the A side, the symplectic analog of this. So that's going to involve quantum cohomology of this variable. And the periodic cyclic homology of the relative Fukaya category. And so homological mirror symmetry tells you that says that these categories are equivalent. So whatever periodic cyclic homology is, it's a categorical invariant. So the same category, so equivalent categories have isomorphic periodic cyclic homology. On the other hand, there's a map OC tilde here, which is Ganatra's cyclic refinement of the open-closed map. It follows from what Nick and I had previously done that this is an isomorphism. And so by tracing around this diagram, going backwards this way and up here, you get this map lambda. And then the key thing, of course, is to show that it preserves all the structure. And perhaps the most important thing is to show that OC tilde respects differential operators, connections. It intertwines, well, the quantum differential operator here and the natural analog of the Gauss-Manin connection, which exists, according to Getzler, in the periodic cyclic homology of anything. Okay, so that's something about the geometry of open-closed maps, and that's the heart of the proof, and that's what Nick will tell you about on Thursday. Okay, thank you.